So good afternoon. Hope everybody enjoyed lunch. I'd like to warmly welcome our second keynote speaker, Dr. Cherine Fahim. And no more than Susan Hart, Cherine has achieved so much in the field that all I can do is give a sprinkle of what she's done. So she received her doctoral degree from the Faculty of Medicine at the University of Montreal, followed by post-doctoral fellowship from McGill University Neurological Institute. She has worked on the relationship between brain and behaviour for many years in universities in Switzerland and New York. Cherine uses neuroimaging tools to investigate brain phenotypes in children, adolescents and adults with neuropsychiatric disorders. She's the founder and CEO of Induced Neuroscience with the aim of making neuroscience more understandable to the general public. Aren't we all happy about that? She has authored, co-authored and been cited by more than 300 scientific journals and has won numerous awards, honours and fellowships. And we're very privileged and delighted to have you here today, Cherine.
Thank you very much. It's my pleasure to be here actually today. Everybody sees me? Okay? Or am I like... It's nice. Okay. So, it's really my pleasure. In fact, I studied neuroscience. I started neuroscience in 2001, and it was really a discovery for me. Neuroimaging. So I did my PhD on schizophrenia, specifically schizophrenia, depression, and bipolar disorder. And then at that time, I had my first child, who is now 17 on the 6th of May, 17 years old. And then I was so interested because I was before Montreal, I was at Columbia University and I worked in genetic psychiatry. And I was very, very interested in genetics and the effect of genetics specifically on building, learning, and memory. So I had my first child, everything went okay. And then for my postdoc, I worked on the Quebec newborn twin study, where we had to scan 1,672 pairs of twins. It was huge. I stayed like days and days scanning these twins. It was so cute, but it was so hectic too. 6 months after that, I was pregnant with my twins. And this was the epigenetic part of it. And I said, okay, so it's not only genetic. I mean, we're built in, yes, genetically from my father, my mother, but we also have this epigenetic. And then after that, I told my husband, okay, you sleep in a room, I will sleep in another room because we have lots of twins to scan. And I will another twin. So I have 3 kids, and in addition to, like what Catherine said, I'm a proud mom of 3 kids. Okay, today what we will discover together is what are really the building blocks of learning and memory. So, the life of a memory. What is the life of a memory exactly? How does it grow? What neuroscience says about that? Oh, trauma. How do my neurons perceive you? Pruning. What is pruning? And actually, pruning is a blessing. Pruning is a good time to meet with oneself. 3 times. My neurons on psychotherapy. What do they tell me? Yes, you can. And take home message. We have an hour. I hope we will get through. Before all that, it's nice to watch together a brief video, 4 minutes, less than 4 minutes, on what we will be discussing.
Learning to deal with stress is an important part of healthy development. When experiencing stress, the stress response system is activated. The body and brain go on alert. There's an adrenaline rush, increased heart rate, and an increase in stress hormone levels. When the stress is relieved after a short time, or a young child receives support from caring adults, the stress response winds down and the body quickly returns to normal. In severe situations, such as ongoing abuse and neglect, where there is no caring adult to act as a buffer against the stress response stays activated. Even when there is no apparent physical harm, the extended absence of response from adults can activate the stress response system. constant activation of the stress response overloads developing systems, with serious lifelong consequences for the child. This is known as toxic stress. Over time, this results in a stress response system set permanently on high alert. In the areas of the brain dedicated to learning and reasoning, the neural connections that comprise brain architecture are weaker and fewer in number. Science shows that the prolonged activation of stress hormones in early childhood can actually reduce neural connections in these important areas of the brain at just the time when they should be growing new ones. Learning to...
Okay, so this is stress. And stress is really very, very important. We cannot talk about trauma today without talking about stress. We all definitely have things that we really want to forget. Definitely. Everybody, okay? Specifically traumatic experiences, okay? But however, erasing these memories that we want to erase had always been science fiction. I mean, there are a lot of movies talking about erasing these memories that we will talk about today, that it's not really science fiction, we're approaching that. After all, what happened, happened. Some people would say that. It's okay, after all, what happened, happened. And your experience is solidified in your head as part of your past and perhaps molding your personality, and nothing can change this. But does it really have to be this way? Do our all traumatic experiences really have to be set on our neurons, as we will see, and never go away? Traumatic memories may also enrich our existence and make us more resilient. So even traumatic memories, they have their positive impact, and they can have their positive impact on us. And they are very enriched with, not only with the memory itself, but with what, where, when, and the contextual information. And every time, this is a very important information for the rest of the talk, every time we retrieve this memory, and the retriever of this memory is triggered by similar experiences. And this is why I worked in several psychiatric hospitals, in New York Psychiatric State Hospital and Liège-La-Fontaine in Montreal. And actually, every time the patient was re-administered in the hospital, there was a trigger. It's not based on that traumatic experience, like 20 years ago, that he is hospitalized. No, it's just there was always a trigger that made him remember what happened 20 or 30 years before. And this trigger will retrieve the whole memory again and again. But how does it happen in the brain, exactly? How is it going on in the brain? Let's watch.
Think back to a really vivid memory. Got it? Okay, now try to remember what you had for lunch 3 weeks ago. That second memory probably isn't as strong. But why not? Why do we remember some things and not others? And why do memories eventually fade? Let's look at how memories form in the first place. When you experience something, like dialing a phone number, the experience is converted into a pulse of electrical energy that zips along a network of neurons. Information first lands in short-term memory, where it's available from anywhere from a few seconds to a couple of minutes. It's then transferred to long-term memory through areas such as the hippocampus, and finally to several storage regions across the brain. Neurons throughout the brain communicate at dedicated sites, called synapses, using specialized neurotransmitters. If two neurons communicate repeatedly, a remarkable thing happens. The efficiency of communication between them increases. This process, called long-term potentiation, is considered to be a mechanism by which memories are stored long-term. But how do some memories get lost? Age is one factor. As we get older, synapses begin to falter and weaken, affecting how easily we can retrieve memories. Scientists have several theories about what's behind this deterioration. From actual brain shrinkage, the hippocampus loses 5% of its neurons every decade, for a total loss of 20% by the time you're 80 years old, to the drop in the production of neurotransmitters like acetylcholine, which is vital to learning and memory. These changes seem to affect how people retrieve stored information. Age also affects our memory-making abilities. Memories are encoded most strongly when we're paying attention, when we're deeply engaged, and when information is meaningful to us. Mental and physical health problems, which tend to increase as we age, interfere with our ability to pay attention and thus act as memory thieves. Another leading cause of memory problems is chronic stress. When we're constantly overloaded with work and personal responsibilities, our bodies are on hyper alert. This response has evolved from the physiological mechanism designed to make sure we can survive any crisis. Stress chemicals help mobilize energy and increase alertness. However, with chronic stress, our bodies become flooded with these chemicals, resulting in a loss of brain cells and an inability to form new ones, which affects our ability to retain new information. Depression is another culprit. People who are depressed are 40% more likely to develop memory problems. Low levels of serotonin, a neurotransmitter connected to arousal, may make depressed individuals less attentive to new information. Dwelling on sad events in the past, another symptom of depression, makes it difficult to pay attention to the present, affecting the ability to store short-term memories. Isolation, which is tied to depression, is another memory thief. A study by the Harvard School of Public Health found that older people with high levels of social integration had a slower rate of memory decline over a 6-year period. The exact reason remains unclear, but experts suspect that social interaction gives our brain a mental workout. Just like muscle strength, we have to use our brain or risk losing it. But don't despair. There are several steps you can take to aid your brain in preserving your memories. Make sure you keep physically active. Increased blood flow to the brain is helpful. And eat well. Your brain needs all the right nutrients to keep functioning correctly. And finally, give your brain a workout. Exposing your brain to challenges like learning a new language is one of the best defenses for keeping your memories intact.
Okay, all this is really good. And it talks a lot about neuroplasticity and how we can manage to get more neurons and based on the 2 neuroscience laws, use it or lose it, or what fires together wires together. Okay, this is great. But however, all this will not talk about traumatic events, because even when we are stressed, we still remember so much our traumatic events. They don't disappear. They don't get fade away. So how does this happen in the brain? What is really the life of a memory? In neuroscience, memory research is suggesting there might be a way to turn back the clock. What seems centered part of our identities can be changed. You saw, like, the more the 2 neurons talked to each other, the more they became friends, and nobody will forget the other one. But would they be able to be disintegrated from each other's or forget that were friends? Memory, they take part of the hippocampus. At the beginning, memory is not really in the hippocampus. Like, memory is where? Where the memory, the first place where memory is where? The frontal, right? The frontal. Why? Because the frontal, I like very much the frontal cortex, because the frontal cortex is the big boss, okay? So for me, really, the frontal cortex is the big boss. A lot of the things we have everywhere in the brain, we will see that they are replicated again in the hippocampus. But when we need to take a decision. Like memory, it's all over the brain, as we will see, specifically in the hippocampus. And we call it the hippocampus because it resembles really the hippocampus, which is a magnificent sea, of the sea. So it takes place in the prefrontal cortex, short-term memory. This is where is the short-term memory. But this short memory, it's where the big boss is, because it's the big boss who can say, okay, this is an important information. Overnight, you should get it into the long-term memory. Or the big boss would say, no, this is not an important information, recycle it. I don't need it. So this is why it's short-term memory, it's in there. So this is short-term memory. We get anything like what you're hearing from me now with short-term memory for an hour, okay? But your prefrontal cortex would decide, okay, what Cherine is saying is important. I will this night get it into the long-term memory. Oh no, what Cherine is saying is not that important. I will just recycle it, okay? So this is what happens every time. And when we hear something or when we use learning and memory, hippocampus and the hippocampus doesn't act alone. It needs really the cortex, which is, I mean, when we talk about the cortex is, you saw the brain, huh? Everybody knows the brain. So it's, the cortex is the very truncated, like sheet-like part on the upper brain, okay? So this is the cortex. So the memory is all over this cortical layer, which we call cortical layer, okay? And also in the amygdala. Why? Why memory is that important? It's really everywhere. We cannot say that memory is in the hippocampus only. It's episodic memory. Episodic memory, yes, it's in the hippocampus. But memory is all over, as we will see, that also other parts are responsible for memory, specifically this part, the basal ganglia. So the basal ganglia part, which is deep, very, very deep inside the brain, this is the gray matter, and this is here all the basal ganglia, deep gray matter. Why? Because the deepest gray matter would permit to an Alzheimer's person who lost approximately more than 20% of his hippocampus to wake up in the morning, take the car keys, and drive his car. What? He didn't forget how to drive the car? No, he didn't forget. How? Because driving the car is in the basal ganglia and not in the hippocampus. So this is a very important thing. Okay, we have lots of information inside the brain. It's not only the hippocampus. If we lose the hippocampus, we lost it. Oh, we lost everything? No, we didn't lose everything. What we learn, musical instrument, basal ganglia. Aerobics, sports, basal ganglia. Skiing, basal ganglia. Everything you do with your hands, basal ganglia. This is very important. However, unfortunately, yes, traumatic events are in the hippocampus. Not only the hippocampus, the hippocampus would only be the index, but it's everywhere in the brain. But also, it's very, very hippocampus-like. Why? Because the hippocampus is closely related to an area here, which is the amygdala, as we will see it. And the amygdala is where our alarm clock is, or the alarm. So every time we have a negative information, it's our alarm system, which is the amygdala, would be turned on to tell us, oh, there is a problem. There is a problem, and this problem, you should deal with it. So deal with it quickly. This is the amygdala here. It's good and not good that there are very, very much friends. It's good because I'm walking, okay, here we don't have bears in Switzerland, but imagine you are in Canada and you have a grizzly bear in front of you, walking in the forest, and you have a grizzly bear, okay? So the first thing that will turn on inside your brain is your amygdala. Here, these two, we have two, amygdala. Okay, so the amygdala would be on to alarm you, okay, just do anything now, but just try not to run, climb on the tree, or do as if you're dead, okay? So this is the amygdala that would say that. And the amygdala would get its information from the hippocampus. Okay, my mom told me if I'm just like in the forest and I saw a bear, I should do this, okay? So this is why they are so related. The amygdala at this time, during traumatic events, would not go and ask the big boss to try cognitively to assess the bear. Oh, he's cute. He's brown. No, I think he's not brown. No, I don't need that. So I don't need at all the prefrontal cortex to be on. I just need it to shut down. And this is why when we panic, we cannot cognitively think. Because the prefrontal cortex, he's the big boss. Yes, he's the big boss, but I don't need it now. I just need my memory information. And this is why, and this is the problem, that every time I face something similar to a traumatic event, or even I watched a movie on a traumatic event, the amygdala would again set the alarm, and the hippocampus would be on, and I would remember everything happened. So this is retrieval. Every time I would retrieve the information. I pass by encoding, consolidation, and retrieval. Okay, this is like every time I pass through these. Memories are not stored as they were initially encoded, but rather they undergo a gradual reorganization process, right? car accident or a movie, and I have my best friend, which thinks almost like me, and when we go out from the movie, she would remember some stuff, and I would remember others. So memory is not, it's not fidel, it's not really the same every time. Why? Because every time I learn a new thing, my hippocampus would compare it to my old memories. There is always a comparison, always a comparison. And there sleep plays a very important role. The more we sleep after a memory, the more the memory would be consolidated. And this is why starting by age, I'm 47, okay, so I'm not that old yet, but like starting 80, for example, my father is 84, and 84, I noticed that he has more naps. Like along the day, he needs to sleep like children. Why? Because every time we nap, we consolidate memory. Every time we nap, we consolidate memory. This is very important. And there are two models which we consolidate memory. Either it's hippocampal neocortical, so it's either the hippocampus would always talk to the cortex, hippocampus cortex, the whole cortex, and this cortex is really very, very important. The cortex, it's in neuroimaging, we usually measure the cortical layer, and we have 6 cortical layers. If we unfold, the cortex is 6 meters. It's huge, huge. But nature was fair enough. Said, okay, I will not let them like go and walk with 6 meters. No, just unfolded, folded the cortex until it fit in our head, thanks to nature. Or hippocampal, neocortical, all synaptic homeostasis, equilibrium also. So it's the synapses that when we will see. This is how we, every time when we are awake, it's always the cortical cortex who would high frequency talking in high frequency with the hippocampus. However, when we sleep, and this is why it's very important to sleep, very, very important. When we sleep, we have the hippocampus, which will talk more to the cortex. This is how we consolidate memory. This is how we consolidate memory. And this was a very important information in neuroscience, because some people used this to say, oh, okay, so we can play on memory while sleeping to let this person retrieve memory or delete memory, as we will see. So, what do we need? We need synchronization while we sleep. We need delta waves, but we also need what we call sleep spindles. You know what sleep spindles? I always joke with my husband because he always tells me, you have a lot of sleep spindles when you sleep. And this is, yes, my husband is a psychiatrist, so he analyzes everything I do. But like, when sleep spindles are really quite interesting. Why? You know sleep spindles, when you sleep, when you start to sleep and then you do like that? Okay, this is sleep spindles. Why? Sleep spindles, and kids, they have a lot, babies, they have a lot of sleep spindles, okay? So if you have a baby or a kid who has a lot of sleep spindles, means that his neurons are really synchronizing, very well synchronizing. This is something good to have sleep spindles. And usually you will notice you have sleep spindles after a very tough day, a very hard day, when you have a lot to remember, okay? So today you will have sleep spindles. So sleep spindles will help your memory be consolidated inside the brain. And also will help having you with a lot of acetylcholine. And acetylcholine is the neurotransmitter involved in memory, specifically really in memory. Like people with Alzheimer's disease, for example, they take Aricept or rivastigmine as medications, and these medications, they contain acetylcholine. Okay, so once encoded, this nascent memory remains fragile for several hours. And this is quite important, okay? For example, in what we can use actually now, once we knew this very, very important information, that for several hours this memory is very, very fragile, is that after a rape incident, for example, or other traumatic incidents, in several hospitals, what we give is a boost of benzodiazepine. And benzodiazepine, what do they contain as a medication? They contain GABA. And GABA is an inhibitory neurotransmitter. So GABA would inhibit the acetylcholine and would stop the memory formation. But this we have to do in the hospital, because this is like giving a lot of benzodiazepine, the patient could just like, not the memory would go away, but the whole patient. So it's very, very important to be really careful of when giving benzodiazepine. But this is something that we can do. With age, why with age these memories of traumatic events, they don't fade away, they don't go? This is also something very important. Here we have the hippocampus, okay, which contains like a lot of acetylcholine, and during sleep this hippocampus talks a lot to the cortex. Okay, this is very good to make memories stay. When I was young, my mom told me every time I had an exam, okay, just revise before you go to sleep or in bed. Just revise in bed. Why? Because she didn't know, but like instinctively, the brain knows that really what we repeat before sleeping would always let the hippocampus talk to the cortex and the memory would stay. However, with age, this decreases. But why memories? It's totally the opposite. They actually become more and more evident with age. Specifically, by the age of 50, like for 40 to 50, our traumatic memories, they may again arise. We will see why in a moment. So this means that we have different kinds of memories. Yes, we have the episodic memories, episodes of our lives, or semantic memories, which are really in the temporal lobe, specifically in the hippocampus and all over the brain. But we have also procedural memory. We said, okay, skiing, playing an instrument, musical instrument, have a lot of old people who have dementia, okay? But when we give them their guitar or piano, they would play the music they played when they were young. Why? Because musical instruments, they are in the procedural memory. And what we discovered is that, unfortunately, what would also remain in this procedural memory here in the basal ganglia are also fear conditioning, okay? You always know like what is conditioning. Pavlov, classical conditioning, that's the problem. So classical conditioning and Pavlov and associating two events, they are extremely traumatic, take also part in the basal ganglia, and this is why it's very important for them to be deleted or fade away. Difficult, but not impossible. So memory formation is like the way foot traffic creates a path along like a stretch of grass. Okay, imagine that this is your neuron here, okay, and every time you repeat the memory inside your head, even internally, every time you repeat, you have this pathway engraved in your memory, engraved in your brain. Because if you had one traumatic event and you don't think about it, but not really put it unconsciously, this is very bad. But to explain it to yourself differently, this pathway would be also different. So this pathway is your neuron. This is your neuron, okay? This is the gray matter, okay? So this is the whole neuron, the gray matter, and gray matter is relatively under genetic influences. This is gray matter, okay? But you have a lot of advantage on your white matter, because your white matter is along the axon here, and your white matter is relatively under epigenetic influences. Every time you learn something, you augment the amount and the volume of your white matter. Every time you learn something new, every time you memorize something, every time this here, your white matter is getting bigger and bigger and bigger. And this white matter may prevent genetic information to take the load, okay? So this is important because it's important also for the trauma. A lot of people experience traumatic experiences in their life, but to be or not to be traumatized, okay? Cumulative stress, the accumulation of stressors across the lifetime, and this is basically epigenetically, or the environment would make you at risk. However, you have also specific susceptibility genetically. I have traits, personality traits, for example, from my mom who is very anxious. Okay, I have personality traits, I'm anxious. I'm anxious, and this would make me genetically susceptible to anxiety traits, okay? And the environment would come and add to this, and I can develop depression, for example. When I scanned, but it was not on the postdoc, but during my PhD, I scanned twins, girls who were 21 years old, and one had schizophrenia postpartum. So after giving birth to her first son, just 2 days after giving birth, she tried to kill the baby several times, by all means. And she developed schizophrenia. She was 100% sure that this is the devil, and she had to kill him. So when we scanned both sisters because they were monozygotic twins, so they shared 100% of their genes. Okay, how? And the other one was pregnant. So I said, this is great, because once she gave birth, we would know if she would develop schizophrenia or not. The other one gave birth, and she didn't develop schizophrenia at all. And we followed her for years after that. And then we wanted to know, okay, what did happen to this girl who developed schizophrenia? Before developing schizophrenia, she was addicted to everything you can imagine. All drugs, alcohol, everything, okay? Maybe this was a predisposition factor, okay? Because this augmented the dopaminergic levels in her brain, okay, maybe. No, not only. And when we talked about the mother of the twins, she said, okay, I will tell you, but actually, when she was young, when the two girls were young, I took this one always to work with me. She was an attendant in the school. She took one girl, the normal one, to school every day with her, and the other one she left with the neighbors. And the neighbor, 60 years older than her, and who raped her for several years. And then by the age of 12, she started addiction, and then started like all kinds of addiction, and then at 21 she gave birth and developed postpartum depression. Okay, so both the grandmother was schizophrenic. Both monozygotic twins had genetically the susceptibility to develop schizophrenia. Yes, because genetically they have 100% of their genes. So both they had this genetic. However, the twin who developed postpartum schizophrenia, environmentally, there was an adverse life event, a lot of adverse life events, who pushed her here not to depression but to schizophrenia. Maybe first depression by 12, this is why she got addicted, but to schizophrenia at the end. This means that it's not only genetic, and it's not only environmental, it's both. It's both, and we will see after that there is a third component also of that. This we experienced in a lot of studies in monkeys, for example, and we saw that maternal separation is a very traumatic event for monkeys, and it totally disturbs even the genetic, through epigenetic mechanisms, the serotonergic system, which would let the monkey develop schizophrenia after that. In neonates, they were negative emotionality, very high negative emotionality, and very low activity. Social competence and aggression, very high aggression. And adults also. So it continues in monkeys. Not only in monkeys, we also witnessed that in rats. So the hippocampus, for maternal separation, the hippocampus would get shrunk. The hippocampus is really small. In rats and mice, we experienced maternal separation. You can imagine also for humans. So these adverse life events with prolonged separation or brief separation, and it totally the size of the hippocampus was really different based on prolonged maternal separation or brief separation. However, if we say, okay, but now we know that it's not the environment epigenetically can act negatively, but it can also act positively. Positively, okay, so said, okay, environmental enrichment, protected against the effects of maternal separation. Exposure to environmental enrichment can beneficially influence the behavior. Once we put them again with their mothers, once we put them again in an environmentally enriched sports, for them it was like the ball that they roll on, for rats, for example. And again with mothers, we saw that the hippocampus, and actually the hippocampus is one part of the brain which is under neuroplasticity, and where the neurogenesis of new neurons also can take place in the dentate gyrus. So here in the hippocampus, we saw that there are some new neurons, not only connections, not only brain connections, but actually new neurons that they are growing in the hippocampus. Okay, monkey, rats, but about humans. Early sexual, here, this time it's not only maternal separation, but sexual trauma before the age of 10. Exposure and neuroresponse inhibition in adolescents and young adults, trajectories of frontal theta oscillation. What are theta? We have 5 brain waves, okay? 5 brain waves. You know, when you're watching a movie and you have these, somebody's dying and you have waves, and then when it goes, he's dead. So this is like the brain waves. So we have different brain waves, and the theta ones are very important for the go, no-go task. Okay, when you play, for example, Uno. Everybody's Swiss here? No? Uno? Everybody knows Uno? Yeah. Okay, good. So when you play Uno, okay, you have, your brain is going onto this go, no-go task, okay? It's very, very important, and it's a very hectic task on the brain. Uno is not, it's really serious, huh? So when you play it, it's really go, no-go. When you just say, okay, this is red, oh no, I shouldn't put green, this is a no-go. No-go, it shouldn't go, okay? So this is when normally your theta waves are telling your prefrontal cortex, no, don't go. Don't go because this is not the right answer. However, for these children, it was really problematic. Here with trauma exposure, it's as if it's an image from the brain. Here you see the nose, the brain from above, okay? So this is the prefrontal. Frontal here, frontal parietal. Frontal. They don't have this theta no-go task. They always would say yes. They would go. They would be extremely submissive for everything in the environment. And also they have this GABA inhibitory system impairment, because what impairs, what tells me, no, Cherine, don't go? It's the GABA. It's the theta, yes, but it's the GABA also. The GABA is the neurotransmitter, the most inhibitory neurotransmitter in the brain, would tell me, no, don't go. So they have this, and the frontal theta also is very, very disturbed. And slower rates of change in no-go frontal theta, increased risk for alcohol use in these children because there is no-go. Okay? So whenever their friends are telling them, come on, just let's drink 1, 2, 3, 4 more bottles, they wouldn't say no. So this is alcohol use and psychotherapy and psychopathology also. The influence of the interaction between this and the serotonin genes also would create depression, anxiety, reduced inhibitory feedback in the medial prefrontal cortex, and here specifically in the amygdala, which when we talked about the amygdala, we said that this is our alarm in the brain. Okay, but we said it's not only genetic and it's not only the adverse events. We have this 3-hit concept, which is really quite remarkable. This 3-hit concept is fundamental for understanding how we can either be prepared for coping with our traumatic event or unable to do so and succumb to stress. If we are unable to do so and succumb to stress-related mental disorders, we are in the no-go. We are in the theta waves. This 3-hit concept, okay, we have this. Genetic predisposition, okay. Early environment, okay, adverse events or good events, we don't know. But this is here, later life environmental concepts, and this is what I personally put more into the psychotherapy. Or good friend. Or me wanting to change in my life. This is really the positive aspect in the 3-hit concept. Coping with life to come and remain resilient. And here we have this 3-hit concept. So genetic predisposition with all the genes that would predispose us as the twins. Okay? For the twins, for example, the twin who didn't develop schizophrenia and who gave birth normally to her son had all this. Yes, but this predisposition, genetic, was not turned on by an early environmental adverse event. Genetic, obstetric complications, malnutrition, rearing environment, or others. And either vulnerability or resilience. I mean, for me, there are millions of definitions of resilience, but for me, really, resilience is to accept our vulnerability. It's to accept, actually, that we are vulnerable and we have to work on this. Okay, what about post-traumatic stress disorder? In this article, of PTSD, they said, okay, PTSD normally is based on, first, on fear conditioning, that we are conditioned based on this event, which would create a circuit dysregulation inside our brain, specifically prefrontal limbic systems, and that we will have a lot of flashbacks, dreams, thinking about the event. So every time we retrieve, every time we think we have this memory reconsolidation, and every time we have this memory reconsolidation, it may play with our genetic predisposition. However, fear conditioning is not always the same in the brain. Here you see, I mean, the complexity of PTSD is extremely complex. The post-traumatic stress disorder, now we have lots of wars, rape or violence, which may cause post-traumatic stress disorder. It's very complicated in the brain, and it's not like, we cannot compare it with, for example, social anxiety or generalized anxiety or phobia. It's very, very much complex in the brain, more than other types of traumatic events. We said, okay, if we take, for example, a car explosion. I was in the car, or I just saw the event, but after that, I developed PTSD based on this event. Okay, what will happen to me is, okay, the first thing is the amygdala. The amygdala would say, oh my God, car explosion, and would be on. And it would start talking to, the first thing the amygdala would talk to is the lateral hypothalamus. Increased heart rate, increased blood pressure. Okay? Dorsal vagal nerve, bradycardia, an ulcer, maybe if we don't do anything, ulcer. Brachial nerve, fainting, respiratory distress. I cannot breathe. Basal forebrain, arousal, hypervigilance, and attention. With all that. The nucleus, increased startle response. Every time I hear, even not an explosion, but this, I get startled. And central gray matter, freezing, decreased social interaction. I'm going to corticosteroid release, and the cortisol all over my body and my brain, and cortisol is neurotoxic to the brain. Okay, this is all the amygdala would do, and would remain, the information would be remained in the hippocampus, and the hippocampus would try to convince the big boss that always there is danger everywhere. Everywhere there is a danger. This process, we can play with it, or we can stop it. When? The process during which reactivated the memories are stabilized, again, is called reconsideration. So we have consolidation, this is what happens when we consolidate memory, but we can also reconsolidate them. Reconsolidation occurs most readily after brief reactivation, which strengthens the long-term memory. Every time I reactivate my memory, what happened, it's as if my brain will redo the same way again, the same path inside. This is why every time I retrieve my memory, I reconsolidate it. I make it more stronger and more durable inside my brain. So what is really very interesting is that once I repeat or I reconsolidate the memory, this is when I should analyze what happened. And instead of just keeping the amygdala activated, I would say, okay, it's good. At least I got out of the car. It's good. At least I wasn't in the car. It's good. This is something that happened, and it will not happen again. Or even if it will happen again, I will be more attentive next time. All this is another kind of retrieving memory, because I'm retrieving my memory, but I'm analyzing it. Not only retrieving it and getting just rumination inside my brain. No, I'm retrieving it and I'm analyzing it in another way. What I just told you about benzodiazepine and sleep, and that after a very hard time or traumatic event, I could make people sleep, and while sleeping, I would give them a huge dose of benzodiazepine. This was done recently by a colleague at Douglas Hospital in Montreal, And then they gave Propofol. So Propofol induced deep sedation. It's deep sedation, so it's like benzodiazepine or also anesthesia. Reduces emotional episodic memory reconsolidation in humans. So they made them watch really horrible movies, very traumatic events, or made them remember traumatic events that happened to them. And before sleeping, they gave them this Propofol. And they discovered that, okay, actually, one dose of Propofol following memory reactivation selectively impaired subsequent emotional episodic memory retrieval in a time-dependent manner. Personally, I wouldn't do it. Personally, I wouldn't agree to do it. I think even traumatic events, it's important to remember them. I wouldn't be in this either science fiction, which we use a lot through MEG, magnetoencephalography. Nowadays, also we can use MEG to or TMS to specifically target certain brain regions to make them forget the traumatic events. I think every bit of memory inside us is meaningful and is important, either for resilient or to learn not to repeat it, or to get some sense out of it. But just use Propofol to make us forget this, I don't know, we can discuss it later, but certainly I'm not a fan about it. It's good that we have neuroplasticity, and this neuroplasticity, we can use it instead of Propofol. Okay, so this neuroplasticity, I heard a lot of patients saying, if I'd known when I was in therapy how our precious brain work, how we should take the reins and ride through the landscape of our minds, fertilizing the land to grow healthy brain cells, new brain cells, would I have reached this state of inner peace sooner? It's true. Get to know your brain. Get to know which parts work or which parts they don't really work. And we have these brain buddies, which I really like them so much, our neurons. Actually, we have 10% of our neurons only in the head, not 10% of our neurons. We have 100% of our cells, but 10% of these cells are neurons. And 90% are glial cells. And glial cells are of huge importance in the brain. So these glial cells, they always help the neurons. So the neurons are like the queen and king of our brain. And glial cells are the people, just the people inside the brain. So we have a lot of neurons, and these neurons, they would go to be friends, and glial cells 3 times during our life would come and would make some cleaning. And this cleaning is called synaptic pruning. So synaptic pruning is very, very important in our brain. And this occurs approximately 3 times all over our life by 2 to 4 years old. And this is when we call the turbo twos, okay? So this is when the child starts to say, no, no. No to anything and everything, okay? Actually, the word that is common between these 3 is no, okay? So in 12 to 25, also, when the adolescents start saying no. And 40 to 50, when we start to say to ourselves, no, what did I do to my life? What did I do? Okay, so this is also when we say no, okay? What happens here is synaptic pruning. It's the glial cells who come and just say, okay, now it's time to meet oneself. And to reassess the brain, to say, okay, what should I cut and what should I keep? What it will cut is excess of brain gray matter. So gray matter would go down with age, and no, not with 50 or 40, no, starting at 5, and starting even before. We would see that gray matter would go less and less with age, however, white matter would go much more. So we have much more white matter in the brain between the age of 5 to 40 and plus. More white matter. The more we learn, the more we have white matter. Because, I mean, anyway, gray matter, we're losing it. Anyway, and it's important to lose it. Because, for example, when we don't go through pruning, this is autism and other mental disorders. They don't go through this pruning, so they don't lose gray matter. Normally, we have to lose gray matter to more gain white matter. So gaining white matter is really very important. So we go through a lot of reactivation, rebirth of a memory, and every time you recall the memory, you reactivate it. So pay attention whenever you are reactivating a memory. If you want to delete a memory, don't use proponol. No. Instead, if you want to delete a memory, actually reactivate it and start to get a sense of it. Analyze it. Try to comprehend what is the sense of this memory or even traumatic event. And this is how you can reactivate it and play with your intricate molecular dance with the neurons. They're cute, our neurons, they're really cute. And in a synchronized way, you can reactivate it through working on it. For this, you need motivation, definitely. You need a lot of motivation, but because it's not easy. It's not easy. However, we saw that trauma-focused cognitive therapy or any kind of cognitive therapy and other therapies, either neurofeedback or movement desensitization, EMDR and other therapy has shown very, very promising results in attenuating the symptoms. For example, here, when researchers monitored psychological and spontaneous functional connectivity in PTSD patients, and these PTSD patients were from Italy after the 2002 earthquake. In Italy, we scanned 37 of these patients, administering the social adjustment scale and Davidson chromatic scale and the CAPS also, in order to see and check their functional connectivity before and after the psychotherapy. What we saw is that there were change specifically in increased connectivity. So the connectivity increased after psychotherapy. So here we didn't use profonolol, either a MEG or any other drug. So it was really the psychotherapy alone which increased connectivity between the bilateral superior medial frontal gyrus and the right temporal pole. And this communication, this pathway of communication is huge. It's very important that the big boss, the prefrontal cortex, would communicate and calm the amygdala and the hippocampus. So this way of information is very important. And decreased connectivity between the left cuneus and left temporal pole. The cuneus is here. This is the cuneus. And this is a very, very important part of the brain because this is very self-referential. When I refer everything that happens around me to myself. Oh, it's my fault. Oh, I didn't do this. Oh, anyway, they would say that I'm useless. I will not do anything. When I start analyzing everything that is bad around me to myself. So this is the cuneus, which is very self-referential. So psychotherapy decreased the connectivity between the cuneus and the temporal pole, which was really very interesting. So this is the cuneus and the anterior medial temporal gyrus, and the increased connectivity between the frontal and the hippocampus after psychotherapy. And it was very specific and differently in EMDR and in cognitive behavioral therapy. It was really different. Which means that, yes, psychotherapy may decrease amygdala activity and increase prefrontal dorsal anterior cingulate hippocampus activation. The anterior cingulate is my preferred part of the brain. The anterior cingulate is very, very important because anterior cingulate is the error monitoring of the brain. Really, the anterior cingulate is here, and it's the error monitoring of the brain. So every time you would think about something traumatic or every time you would commit an error, it's the anterior cingulate that should be on, and it will tell you, no, don't do that. It's the error monitoring of the brain. And hippocampus, memory, learning and memory. So psychotherapy acts upon these brain regions, and they may relate to extinction learning and or reappraisal of the traumatic event. We didn't see this only with adult trauma, like the earthquake, no, but also with childhood trauma also. Here, for example, we have the dorso-anterior cingulate in child abuse, which were really getting better also. So it's either adult trauma or child abuse. So, which means that psychotherapy does not only work on what happened recently, but also what happened during childhood. Okay, what do we maintain from all this? Take-home message. Reduced size of the hippocampus in patients who were exposed to abuse or neglect during their childhood, maternal separation or sexual assault. We would see that the hippocampus is reduced. Done? We are predetermined? That's all? No. Because enriched environment, psychotherapy may enhance the amount of neurons in the hippocampus, and we can again regain through neurogenesis. Reduction in GABA also. Here reduction in GABA and the inhibitory system, there was a lot of research also recently between attachment and reduced GABAergic activity and how we can enhance this through psychotherapy. GABAergic system is implicated in inhibition, autoregulation, and self-control, and also metacognition, which is a very important part in counseling psychology. Metacognition is extremely important. An effective treatment for these disorders should selectively decrease these intrusive pathological memories. However, a theoretical obstacle to developing these treatments have been that these memories normally we thought that are relatively fixed. However, with neuroscience now, we know that they are very fragile. And when they are fragile once we retrieve them. And this is the moment that they are quite fragile. And we can use this moment in order to get a sense out of this and get a reappraisal of the situation. Recent research using non-human animals challenges this classical view, who's showing that reactivation of old memory can temporarily turn it to a labile state requiring restabilization process to persist, referred to as reconsolidation, and rendering the memory restabilized, susceptible to manipulation. And this is what we really want as a solution to these traumatic events. And I'm done. Thank you very much.